Welcome to the deep dive. Today we're diving into something really spectacular, something millions enjoy. The science behind 4th of July fireworks. You know, those amazing bursts of color lighting up the night. Our mission is pretty straightforward. Unpack the elemental secrets behind those vibrant explosions. Think of it as a quick way to get smart about something we all love to watch.
Absolutely. And what's so fascinating, I think, is how this huge spectacle, even though it's over fast, is really just fundamental chemistry in action. It gives you these, well, surprising insights into how certain elements behave together and how incredibly precise those reactions have to be to get the visual effect just right. It really isn't just pretty lights. It's more like a controlled chemical dance.
Totally. When you look up, it just feels like pure magic, right?
Mm.
But what's actually going on up there? When you see those incredible colors explode, what's the basic idea, the principle that gives us those different reds and blues and greens?
Yeah, it all comes down to how specific elements react when they get super hot. It's a process called atomic emission. You can think of it like every element has its own unique fingerprint, not just its structure, but the light it gives off. So when you heat up certain metal compounds, their electrons get, excited. They jump to a higher energy level. Then, as they fall back down to where they started, their lower energy state, they release that extra energy as light. And the crucial part is each element releases light at very specific wavelengths. It's those unique wavelengths our eyes see as different colors. It's really atomic level precision.
Ah, okay. So it's not just about burning stuff. It's this really specific electron dance inside the atoms. That's kind of the aha moment for you listening, right? Understanding why the colors are so distinct. Okay, so let's get specific. When we see that really bright, fiery red painting the sky, what elements are doing that?
That intense red, yeah, that's mostly coming from compounds with strontium, or sometimes lithium. They're just really good at consistently giving off light in that specific red part of the spectrum when they get hot enough.
Okay, strontium or lithium for red. What about that bright yellow? The one that sometimes looks almost golden?
That'll be sodium compounds. Think of it, some types of street lamps. Many glow yellow. That's sodium vapor doing that. Same basic idea in fireworks, just much bigger and faster.
Wow, it's amazing how specific each one is, and the range of colors is huge. So orange?
Orange comes from calcium salts, and that really vibrant green you see, that's barium salts. Then for the deep, rich blues, you're looking at copper compounds.
And white, those really dazzling flashes.
Ah, white. That's often zirconium or titanium or sometimes magnesium. They burn really intensely to create that brilliant white light. And, what's really clever is how the firework makers, the pyrotechnicians, handle the purity and the exact amounts of these compounds. Each element needs to be in just the right form, the right quantity, to make sure the color pops and stays consistent. And crucially, to stop unwanted side reactions.
That actually brings up an interesting point. What about a color like purple that feels, I don't know, more complex than just one pure element? How do they make purple?
Purple's a great example, yeah. Shows how they blend things chemically. It's usually not just one element. Typically, it needs a really careful mix of strontium compounds for the red part and copper compounds for the blue. It's all about getting that balance just perfect.
Yeah.
So the two different light emissions mix together in our eyes and we see it as purple.
Right, getting those complex mixes just right, making sure the colors are consistent and keeping everything safe. That can't just be trial and error in a lab, can it? How do the companies making these ensure that kind of precision, when they're making thousands of them?
Exactly. And this is where the engineering side of fireworks really comes in. They use some pretty advanced tools, things like X-ray fluorescence spectrometers. You might hear them called XRF scanners. What's really neat about XRF is that it lets them check the elemental makeup of their mixes without destroying the sample. It can tell them exactly how much strontium or copper or barium or whatever else is in there. So that ensures they hit the exact colors they want, but also that the quality is consistent from one batch to the next. And really importantly, it helps make sure safety standards are met by controlling those chemical reactions precisely. If you sort of zoom out, it just highlights the incredible precision and quality control that goes into something we often just see as pretty lights.
So what does this all mean for you, the listener, next time you're out watching a fireworks show?
Well, it means you're not just looking at a beautiful display. You're actually watching the sky turn into this giant, really carefully controlled chemistry experiment. You're seeing atomic emission happening on a massive scale right above you. So the 4th of July, it's not just celebrating freedom. It's also this incredible demonstration of applied chemistry.
Yeah.
It's beautiful chemistry, really bringing all that color and excitement.
It really is. And maybe a final thought to chew on. Beyond just knowing which elements make which colors, Think about the human ingenuity involved. I mean, not just figuring out these fundamental chemical properties, but then harnessing them, organizing them into these synchronized, explosive, and honestly beautiful spectacles. Kind of makes you wonder, doesn't it? How science is constantly shaping our experiences, often in ways we don't even realize, ways that are just purely delightful. That's a great point. So next time you're gazing up at those bursts of light, take a second. Appreciate the beautiful, precise chemistry that's unfolding. You might even catch yourself trying to spot the different colors and thinking, okay, that's strontium, that one's copper, that's those electrons dancing.